Our first technical talk today is one of our PhD candidates, Brendan Saltaformaggio in computer science. And Brendan is, I've had the opportunity to travel with him, and I find his talk, and it's why I sought him out to be one of our presenters today. He's also won a ton of awards recently, and most recently, probably the most prestigious, as that Brendan has been named one of the 2 Symantec Research Fellows for this next year. So congratulations, and I'll let you talk about your research.
Thank you, Joel. Should be on the mic now. No? Okay. So like Joel said, my name is Brendan Saltaformaggio. I'm a PhD candidate in the CS department here at Purdue. And today I'm going to be talking about some cutting-edge research that I've been doing in the field of cyber forensics, and specifically along the lines of automatically recovering human understandable evidence from memory images of a system under investigation. So most of us, when we think of cyber forensics, maybe the first thing to come to mind is carving old files off of dusty hard drives, right? Well, that's not this talk. Because about 10 years ago, investigators and researchers realized that there is a wealth of digital evidence that gets left behind in the RAM of a system when you're investigating it. And this can be anything from what processes are running on the machine to even some executing malware that might be causing more trouble than the actual criminal, to things like encryption keys for whole disk encryption, and then all of that application data that's being used at that time, right? Your browser histories, your chat logs, and so much more. But the challenge is, as a cyber investigator, how do you recover all of this evidence that's frozen in a computer's memory? Well, when we think of what's in memory, usually the first thing to come to mind is data structures, right? Programming 101, you make some structures, and that's pretty much how all data in memory is stored, organized into some data structures. So investigators first need to find and recover the data structures which store the evidence that they're looking for. Now, this is usually done by immediately collecting a memory image that's a byte-for-byte copy of the physical RAM on the device you're investigating, and then returning to the forensics lab to use memory forensics tools to find these data structures within that memory image. To do this, you first pick the data structure you're looking for. You build a signature for that data structure. That's just a set of constraints that let you find that data structure in all of that raw memory that you have in the image. And then a memory forensics tool takes that signature in, and it's going to scan through every offset in the memory image, finding instances of those data structures that you're looking for. So prior to my work, this was very much the state of the art. Every memory forensics tool out there focused on recovering raw instances of individual data structures from memory images. And that worked pretty well for a long time if you were looking for plain text or self-contained fields within those data structures, like a password field in a user account structure, right? But as we're going to see in this talk, focusing on only these plain text fields in simple data structures is severely limiting the amount of evidence that you can recover from a memory image. And so I'm going to start things off a little different this morning, actually with a crime story that's based on some true events that happened here at Purdue University. Let me jump out real quick and go to the video player because, like we said, Microsoft was not cooperating today. Okay, so about 2 years ago, there was a group of students who were found changing grades for themselves as well as accomplices who paid them for this service. So let's imagine we're watching this cybercrime unfold. The criminal has access to this official grade report, and they're in the process of changing grades for themselves as well as other people who are involved in this crime. But before this would-be awesome hacker has a chance to save the file, law enforcement agents arrive, right? And the first thing they're going to do is image the computer's memory, seize the machine as evidence, and then return to the forensics lab to recover evidence of this crime. Now notice, the only evidence that we have at this point of all of the accomplices involved in this crime is in the memory of that computer. because he hasn't saved the file that he was editing yet, so the grade report that's on disk still shows the original grades. And of course, you're going to get this guy into the university police station, and he's not going to be talking. So, if we can jump back to the slides. So like I said, the state of the art before my work was recovering these raw instances of individual data structures from a memory image. Now, believe it or not, this is that PDF that we just saw being edited in raw data structure form. You can see the problem. Just because investigators can recover raw data structures doesn't help them understand the content of those data structures. You can't see what was edited in this PDF. It's all encoded data. And this same problem arises for all kinds of different evidence that programs are interacting with. Things like images, documents, basically any kind of encoded or formatted data is not going to be plain text or human understandable when it's in raw memory. So we define this as the content reverse engineering challenge in memory forensics. And a recent paper of mine overcomes this challenge by making the observation that if an application defines a data structure, like that PDF data structure, the application must also define some printing or rendering logic for that data structure, right? So for instance, we have that PDF data structure in memory. The program that defined that data structure must also know how to display the PDF. It has to know how to save the PDF to a file. So why can't we reuse that logic to give investigators access to the content of that PDF? So let's imagine that this simple program code is the PDF editor we were looking at, right? It defines that struct PDF that we're interested in recovering, and then the first line loads in a PDF file. It initializes that data structure. The main loop executes while the user makes some edits. And then finally, we have this save PDF file function. Now notice how this works. It takes as input that in-memory raw PDF structure. It formats it, it turns it into a nice human understandable PDF file, and then saves that file to disk. The idea behind DSCRETE, and what we did was remove that piece of code that actually renders the PDF data from memory and turn it into what we call a scanner plus renderer. The intuition behind a scanner plus renderer is that this code, this formatting code, must be very complex. It has strong assumptions on the input, that PDF data structure. So when we present it with just random memory, it's going to cause that code to crash. But if we scan through every offset in a memory image, eventually we'll hit that PDF data structure we're looking for. And for that, this function is going to output the natural application output that would have been created for that PDF data structure in memory. Make sense? So I like to show rather than tell. So I'm going to give you another video that actually shows DSCRETE in operation, recovering that PDF. And I'm going to skip past the first part of this video is just isolating that scanner plus renderer logic. The second half is actually doing the scanning, and that's what I'm going to skip to here. Okay, so like I said, the first part just isolated that scanner plus renderer within the binary. I should note that these are binary techniques that I'm going to be talking about today. We don't require any source code in order to do this. So we've isolated that scanner plus render, and now we're going to use DSCRETE to scan the memory image. DSCRETE just requires that we execute the program until we get to that scanner plus renderer component, and then it's going to take over, and it's going to begin the memory image scan. So here DSCRETE's taken over. It takes about 30 minutes to get through every single offset in that giant memory image, and then when it's done, we can look over the results. As expected, there's only one, of course, because we were only editing one PDF. And we can see, in fact, it is the PDF from memory that has the higher grades on it. So now investigators have a very easy time figuring out who was involved in this crime beyond the one guy who was changing grades. And recall, without DSCRETE, this is the best that existing techniques would have given you, just these raw data structures that are totally unintelligible to human investigators. So we didn't just... Where are we? Let's get back to the slides. So we didn't just test DSCRETE on PDFs. We tested it on a bunch of different types of data from memory that all require complex decoding functions. If you read the paper, there's even more. Things like images from a bunch of different image processing programs. Screenshot, like if you hit print screen, you can actually recover those out of memory. Oh, this is a good test case. These are in-memory request logs from a web server. These have yet to be flushed to your request log on disk. They're just sitting in memory. And of course, they're all encoded, right, with integers. You'd never understand it. But here, investigators get the nice IP addresses and browsers they're using. PDFs, like we saw before. This is another interesting case. So top, you get the system resource usage for all the processes on a Linux system. So when you run top, you maybe only see 15, 20 processes on the screen. But when we ran discrete, we actually found 382 different processes. That's because although top only shows you 15 or 20 on screen, it actually allocates those data structures for every process in the system. And so you can see that in memory, you may get tons more evidence than you would get even just looking at the screen of that application running. Vector graphics like you would draw in XFIG, and there's a bunch more. You can look at the paper if you're interested. Okay, so we've seen from discrete how you can recover application output that goes to a single data structure that's in the memory of an application. But that's just the tip of the iceberg for what's in memory, and especially when we start thinking about more complex devices such as smartphones that have a wide array of onboard devices that are constantly generating evidence being pushed into the memory of these smartphones. And so one thing that immediately comes to mind, right, is smartphone photography. I'm sure almost everyone in the room has used their smartphone to take pictures. It's the most common use of smartphones other than communication. And this goes for criminals as well, like these two teenagers who took selfies of themselves before robbing a bank. This guy also with his stolen gun about to rob a bank. These two guys who found their stolen guns good enough to post on Facebook. Even a teenager who stole a Lamborghini and took pictures and posted it took pictures of himself and posted it with his smartphone. And these are not just a few select cases. You can actually Google criminal selfie on your own and find all of the wealth of these that exist. And to kind of highlight the importance on a more serious note, recently there was a Supreme Court case, Riley versus California. Some of you are probably very familiar with it, where basically the primary evidence that was of importance in this case was photographs recovered from a smartphone that really gave the investigators the evidence that they were most looking for. But as you can imagine, when you take a picture with a smartphone, that photograph, before you snap it off with the camera app, it caches a copy of that photograph in the device's memory. And the same as if you're streaming a video, right, like Skype, the individual frames of that video hit memory long before the Skype application ever gets access to them. And you can think Skype never even saves the video to disk. This is all going off to the cloud, but it is in memory, okay? But probably the most interesting, I'm sure we've all seen this, when you go to take a picture with a smartphone camera, it shows you what the camera's looking at, right? It's a little preview so you can line the shot up correctly. Well, as you guessed, those preview frames are even being buffered in memory before you're looking at them to line the shot up. And so this leads to a very interesting property that photographic evidence is available in your smartphone's memory just as soon as you open an app that uses the camera. You don't even have to take a picture or a video. But of course, like I said, things in memory are not nicely formatted JPEG files. They're nasty encoded data structures that have to be recovered and pieced back together. And so that's the focus of my paper, VCR. VCR actually is going to recover all of the photographic evidence that's in a smartphone's memory. So to do this, VCR takes as input a memory image from an Android smartphone. It then recovers the data structures which correspond to all of that photographic evidence using probabilistic inference, and we'll get to that in just a minute, and then uses automated image decoding techniques to return to the investigators the actual images that were in the memory of the device. Now, the probabilistic inference is important because VCR faces a pretty significant challenge. All of the different smartphone vendors out there, like LG, Samsung, HTC, they're all customizing the Android framework's camera software to their specific device. So for instance, they may add some fields, they may rearrange some fields within those data structures we're looking for, and therefore it's impossible to build data structure signatures ahead of time for VCR because it's going to be working with all these different vendor customized phones. And the consequence there is that when you scan the memory image, you can't actually match your data structure signature to any of the vendor customized data that's in memory. So to overcome this, VCR uses a technique called vendor generic signatures. These are field offset independent versions of the data structure signatures we've seen previously. So instead of requiring fields to be at certain positions, these are only a set of probabilistic constraints on the structure's field values. So like I'm trying to find one. So like the string camera or the PID of the process using the camera. But it has no dependencies on where those fields lie in the data structure. Now, armed with these vendor generic signatures, VCR takes a typical scanning approach where it's going to scan through the memory image and locate any variants of these data structures which match with high probability. Now, this may give us false positives, but then we rely on another observation. Any valid data structures we recover must have the same layout, of course, because they've been compiled one time. So then we find the matches with the highest probability, and we select all of those that have the same field layout with the highest probability match. Make sense? So that allows VCR to handle all the different vendor customized devices. And again, I have a demo of VCR running to recover some actual photographic evidence. See if we can get it. There we go. So again, back at the forensics lab, investigators are going to be working with a memory image from a smartphone. VCR is going to run in this Android emulator that we have here and use the terminal actually to control the VCR app, which we'll see in a minute. I've already, in this demo, loaded the suspect memory image onto the emulator to be scanned. And we're just going to watch the log in the terminal to see VCR run. So the investigator just starts the VCR front-end app. I'm not a UI designer, sorry. Do forensics tools. And then they select the memory image that they want to scan. There we go. And then VCR is going to start scanning. VCR has a quick two-phase scan. The first phase scans through and finds all the matches that are not probabilistic. And then the second scan goes through and finds all those vendor generic signature matches. First scan is actually really quick. The second scan takes about 5 minutes, but we'll skip that. Okay, so first scan's done, second scan's going. 4 minutes later, and now we can review the results from VCR on this memory image. So VCR found 16 frames, 8 preview frames, that's just lining up the shot, as well as 8 video frames. It's using the image decoding techniques right now to decode them. And we'll see in a minute the investigator can literally just swipe through the frames when they're recovered. Give it just a minute. Okay, and so now you can see this is the preview frames. The investigator can swipe through, and you can see that it gives not only the pictures of this guy in a hood running, but it also gives you some kind of temporal evidence. You can actually get the time duration from these images of when this event occurred. And then those were the preview frames. These are the video frames. And there was no photograph taken in this demo, but if you'd taken a photograph also, you'd have seen that there. Back to the slides. Okay, so here's a cool case study. So like I said, these images are actually hitting memory long before the app itself is getting access to them. So for instance, I use Chase Bank. Chase Bank allows you to take pictures of checks in order to make a deposit. Well, sure enough, that check image is hitting memory long before the Chase Bank app is getting to it. And in fact, we recovered a number of check images from my phone's memory when we were doing these tests. There's nothing wrong with the Chase Bank app. They can't help it, of course. The images, when you take it, go to memory first, and then Chase Bank can access it. There's no way currently for Chase Bank to prevent this. It's not actually an attack against Chase Bank, more against the Android framework, but let's not talk about attacks. This is forensics, right? Okay, so we've seen from DSCRETE how you can recover a bunch of different types of data structures, human understandable output, and we've just seen VCR recover a number of photographic evidence, types of photographic evidence from memory. But I'm a human, right? And when I think of digital evidence, when I want to know what a computer is doing, what comes to my mind is a user interface, right? We all interact with our applications through the user interface. And in fact, the user interface has a wealth of different types of evidence, right? Text, images, and all of this stuff is displayed in one concise place. Unfortunately for investigators, GUIs are also the most complex form of digital evidence. Each individual application's GUI is a virtual billboard of all these diverse application-specific data structures that build each little component of that GUI. Internally, an Android app's GUI is represented as a GUI hierarchy tree, which consists of tree nodes. Each tree node may be hundreds or even thousands of different data structures. I'm simplifying it here by just showing you parent tree nodes in blue and child tree nodes in red. Further, each tree node, the actual graphical content that's on the screen of the app is encoded into drawing operations. Each of these drawing operations describes a little piece of the GUI. So for instance, this draw text op is just one line of text. Together, these three ops describe one line of text in a larger GUI component. And you can imagine a full tree of all these draw op lists builds the entire GUI that you're looking at. So it makes sense to focus our recovery on this GUI tree. Maybe we can recover it, do some rendering, and it'll be easy, right? Unfortunately not. Because as most of you know, Android applications do not share screen space. They actually execute one at a time in the foreground while there's numerous other apps in the background. And as soon as you background that app, Android goes through and explicitly frees and nullifies all of this GUI data that's in the app's memory. And this basically disintegrates that whole GUI tree in the app's memory, making all of those individual data structure approaches that we just talked about totally useless here, because they wouldn't be able to find anything. It's all disconnected. But this is where my paper Guitar comes in. Guitar works to actually rebuild the topology of that GUI tree from whatever is left in the application's memory, and then do the re-rendering process for the investigator so that they can look at the screens of all the apps, no matter if they were in the foreground, the background. So the first step is to recover the hundreds of thousands of different data structures that are left in the application's memory that correspond to these trees. And then to reconstruct the GUI tree's structure alone, you can use some pointers that are left in memory. But then you're left with a problem. You've rebuilt this GUI tree so you know kind of the structure, but you have all of these drawing operations that you don't know where they go, because there's no way to recover. Android has gone through and freed and nullified all the pointers between these two. So there's no way to figure out where the actual graphical content goes back onto the screen you're trying to recreate. But we leverage an interesting observation. Each of those tree nodes that we saw earlier describes some geometrical portion of the screen space. And likewise, each of the recovered draw op lists encodes some renderable graphic content that takes up space on the screen. So maybe you see where I'm going with this. My paper Guitar actually pieces back together the GUI like a puzzle. More formally, we find a global best fit of the GUI graphic components to the open screen space on the app's recovered screen. And this can be modeled as a weighted bipartite graph problem where the node fitness between each side is the drawing content that's being fitted into the GUI. And one last demo, I swear. Show you Guitar actually recovering a screen from the, I think it's WhatsApp app, the WhatsApp Messenger. So Guitar runs inside of this modified Android emulator again. And the investigator is just going to start Guitar and again select the memory image they want to investigate. I think this is a memory image from WhatsApp. So Guitar works on every app memory image independently. So you can give it 100 app memory images, you can give it one app memory image, it doesn't care, it'll work on each one in sequence. Yeah, it's WhatsApp. Okay, so it starts by scanning for all of those different data structures that may remain in WhatsApp's memory after the app was put in the background and left for a while before I collected that memory image. It takes about 6 minutes and it recovers, looks like about around 200 data structures here, and then does the topology recovery, and then does the bipartite graph matching that we talked about, and then it actually does the GUI redraw, and the investigator will be presented with the final GUI. So there we go. So the investigator can actually see the GUI of the app as it looked the last time it was in the foreground of the suspect's device. And for comparison, that's a screenshot of the app when it was in the foreground of the device. Now recall that what we recover is in the background. All of that stuff has been freed, and it's available to be overwritten if the app has any background updates or something that it does. But Guitar faithfully recreates everything, at least as it exists in the memory, as it still exists in the memory image. And I have an even more powerful case of Guitar recovering everything as it exists in the memory image. So this is a case study, the Samsung S4 Contacts app, right? So this shows you your contacts. So that's a screenshot of what the app looked like when it was in the foreground of the suspect's device. And then that's the GUI, the Guitar result for it. And you can see it looks probably 90% correct. It is missing a few icons, but again, that's because it was freed. There's nothing we can do. It actually gets overwritten in memory. So Guitar is still able to faithfully recreate it. But in this case study, we also got some extra recovery. And we were really curious. What is this? It doesn't match anything on the most recent screen. Where did this come from? Well, when we thought back, actually, before we looked at the contact screen of that app, we were on the call log screen of that app. And so you can see that actually 2 of the entries in the call logs persisted in memory, even though we had already changed screens and then backgrounded. And Guitar is able to just recreate that because it's still in the memory image and it all pieces back together. And let's keep hammering on Chase Bank. So the Chase Bank app is really pretty well designed. It's very secure. It requires you to put in a password when you bring the app back to the foreground. But of course, the last screen you were looking at before you backgrounded the Chase Bank app was some internal screen, right, after you'd already logged in. And so that's the data structures that Guitar is going to recover. So for instance, this is Chase Bank on 3 different smartphones that we tested, recovering the account screen. Even though it had been in the background, it was already timed out, the app was logged out, but those data structures still remain in the memory. And this was a very proud moment for me. I published this picture in the paper, and I said, Figure 3 shows the author's graduate student-sized bank accounts. So in conclusion, before my work, we were talking about individual data structures, and my work has really tried to bring that into the 21st century with some human understandable evidence. We saw DSCRETE that recovers application output for specific application data structures. We saw VCR, which overcomes vendor customized photographic evidence recovery from smartphones, as well as Guitar, which recovers GUIs that are frozen in Android app memory images. Just before I go, to put this in a larger picture of the research that my group is working on in its entirety. We work on APT, that's Advanced Persistent Threat Style Malware Detection and Forensics. This is all based on integrating both forensics and detection mitigation capabilities. And we come at this from a binary-centric. Remember I said we do not have any source code for any of the work that we do. Our tools rely only on binaries. And we come at it from 3 different angles: temporal, spatial, and behavioral forensics. We're supported by these very wonderful organizations, and we are always looking for more. And if you're interested in any other lines of work that we have to do, we kind of split them, like I said, temporal, behavioral, spatial. You've seen memory forensics, that's in our talk, that's in this talk, and you can go look at our webpage for any of the other work that we've done recently. And with that, I thank you very much for your attention. I'm open to take any questions.
Thank you, Brendan. In the sake of time, Brendan, are you going to lunch with the group today?
Yes.
Very good. Seek Brendan out if you want to learn more about this technology. He will be joining the lunch group.